What we're going to talk about in this tutorial is the ways in which we can represent organic molecules on a plane surface. In other words, how we can write out the formulas. Now, really, it's pretty straightforward, and this is something that we covered pretty thoroughly in lecture. But let me just review the important parts. Okay, probably the simplest way of representing an organic molecule is through something which is called a condensed formula. This is where we just have a series of CHs, CH2s, CH3s all strung together. This method doesn't give us any feeling as to the actual structure of the molecule. It just sort of strings the different methylene and methyl groups all together. Kind of an advance of that is the so-called Kekulé structure. With the Kekulé structure, we actually show the way in which the carbons and whatever substituents are attached to the carbons are hooked up, oriented in space. All right? Like, for example, here we've got a secondary alcohol. This is 2-propanol, and you can see that the OH group is coming off the second carbon. All right. Now, an advance over that is something which we also talked about in lecture, the Lewis structure. And the main difference between the Kekulé structure and the Lewis structure is that with the Lewis structure, we're very explicit about non-bonding electrons. And the Lewis structures are probably going to be the most widely used structures that we use in this course. And the reason for that is because these non-bonding electrons are very important in showing how reactions take place, because very often when you have some sort of a chemical transformation, bonds being formed, bonds being broken, it's these non-bonding electrons which are involved in it. Okay, so these Lewis structures are very important. Now, the other thing, one of the problems with the Lewis structure, just as with the Kekulé structure, is that you get the impression that the molecule is just sort of like smashed out. It's flat, perfectly flat. We know that that's not the case because we've spoken repeatedly about the fact when you've got carbons, they have a definite geometry in 3 dimensions. Okay, for example, with when carbon has all single bonds, it has this so-called tetrahedral structure. So this is really ridiculous because it shows that this indicates that the bond angle here is 90 degrees. We know that the bond angle is actually 109 degrees. So in an attempt to sort of clarify that 3-dimensional structure issue, we have the wedge and dash diagram. Now with the wedge and dash diagram, we actually represent bonds in 3 different ways. We've got just a plain line, which indicates a bond which lies in the plane of whatever it is that you're writing the structure on, in this case the screen here, or a piece of paper, or the page in the book. A solid wedge represents a bond which is projecting out of the plane, all right? And this dashed bond represents a bond which is projecting behind the plane. So this is a kind of a rudimentary way of attempting to deal with the 3-dimensional structure of these molecules. Another way in which we attempt to deal with 3-dimensional structure is the so-called sawhorse, all right? And through perspective, this is not particularly well drawn, but there are better examples in the book. Through perspective, you get the impression that bonds are projecting behind the plane, out of the plane, and in the plane. All right, so this is a kind of a less explicit way of giving the same information as these wedge and dash diagrams. Now, these are all well and good, and these are methods that we're going to use repeatedly throughout this course. As I said before, we're going to rely heavily on the wedge on the Lewis structures, and we will also be using this wedge and dash. There's one problem with these structures, particularly structures which are comprised entirely of single bonds, and that is the fact that they don't take into consideration the fact that the molecules are dynamic. In other words, we know that around single carbon-carbon bonds we have free rotation. So the impression that you get when you look at this structure or even this structure here is that these things are really locked in space. They are not. All right, these bonds are constant, or these substituents here, these 2 carbons are constantly rotating through 360 degrees relative to each other. Turns out that this orientation, this sort of instantaneous orientation, can be very, very important in predicting the outcome of a reaction. All right? And in order to cope with that problem of dealing with that, there's yet another type of representation of molecules. It's referred to as a Newman projection. Okay? Now, let's start off with a very simple molecule. Let's start off with ethane. All right, and what we're going to do is we're going to take a look at how we can depict the rotation of one carbon around the other carbon. In other words, rotation around this single bond joining the two of them together. So in doing that, what we're going to do is we're going to take this molecule and rotate it 90 degrees out of the plane of the screen in this case. Okay, so we're going to take this and rotate it out. Okay, now carbon 1 is going to be represented by this symbol here. All right, this is sort of like like the blades of a propeller. All right, and the idea is that this intersection here of these three lines, these three bonds, this is the actual carbon. Okay, so this intersection here represents carbon 1. Now, the second carbon, in other words, the carbon behind this, is represented by an open circle, and we've also got bonds projecting out of that. So this open circle would represent carbon 2. Okay? Now, we put the two of them together. So in other words, what we're going to do is we're going to take carbon 1, just sort of paste it right on top of carbon 2, and this is the result that we get. All right? So this is a simple Newman projection of ethane. All right? Well, we've got carbon 1, then we've got carbon 2, and we have the bonds for the various substituents coming off at these dihedral angles. All right? Now, you notice that in this case here, we've got everything staggered. All right? In other words, all these bonds are more or less uniformly spaced away from each other. There's a uniform radial interval between all of these bonds. All right? And as the structure suggests, this is what's referred to as a staggered conformation. Now, as we said at the outset, you have free rotation around this bond. So what will happen is that periodically, this thing will rotate through yet another conformation. Incidentally, let me just emphasize that terminology. When we refer to any of these particular types of configurations, it's referred to as a conformation. All right, so this would be the staggered conformation. This is where you've got the substituents on the two carbons as far away from each other as possible radially. Okay. All right, now, as I said, you have free rotation, so it's reasonable to expect that at some point they're going to rotate into a conformation where they're perfectly aligned. All right? And this is referred to as the eclipsed conformation. So when you've got the substituents on the two carbons perfectly lined up, this is referred to as an eclipsed conformation. Now, these are the two extremes. All right? Obviously, you've got a whole spectrum of locations which are intermediate between this and the staggered. Which one is the best? In other words, which one does the system actually prefer to spend most of its time in? Well, in order to understand that, we have to take a look at the consequence of this structure here. In this structure here, we've actually got these bonding electrons very close to each other, or as close as possible to each other. And it turns out that there's a certain amount of repulsion between them. Right? So this actually represents the energy maximum. This conformation here, this eclipsed conformation, has the highest potential energy, and therefore it's least favored. All right? And what we can do is we can actually make a plot of potential energy of the reaction as a function of the degree of rotation of one carbon around the other. So if we start off with a 0 degree at 0 degrees here, in other words, where we've got a perfectly eclipsed conformation, in other words, we haven't rotated either of these carbons, this would represent an energy maximum. Now, if we take one of the carbons, it could be either carbon 1 or carbon 2, and rotate it 60 degrees, all right, what we do is we enter into the staggered conformation, and this would represent an energy minimum. All right, this is going to be the most favored conformation. But the thing is, it doesn't stop there, because obviously we can rotate each of these carbons through 360 degrees. So if we go another 60, wait a minute. Yeah, if we go another 60 degrees to 120, we go back into another eclipsed conformation and the resulting energy maximum. If we rotate it yet another 60 degrees, we go to 180, and then we go into another staggered conformation, etc. All right, I'm not going to bore you with going all the way out to 360 degrees. But this is the one way that we can use, the one method that we can use to represent these kind of instantaneous orientations of one carbon substituents relative to another. And as I said before, this is going to be quite important as we go through the course. All right, now we started off deliberately with the simplest molecule to which this applies. I mean, obviously, in order to analyze conformations, we have to have at least two carbons bonded together. I mean, to do a conformational analysis of say, methane is ridiculous. It's meaningless. One thing that I would like to do at this point is plug our model kit. You can get a very, very good idea of this by using your models. All right, so find your model kit. All right, take the cellophane off if you haven't already done so, and just sort of play around with this. All right, so in this case here, this would represent the eclipsed conformation. All right, we take this and rotate one of the carbons 60 degrees. This would represent a staggered conformation. Now, I want you all to do this. Is that understood? All right, play with your model kit. All right, so this is a kind of a neat way of sort of verifying this whole Newman projection thing. This Newman projection approach to representing the molecules. All right, now, as we start adding more and more carbons onto a molecule, this conformational analysis becomes more complex, more involved. All right. So let's take a look at, let's go up one step in terms of, well, actually two steps in terms of complexity. Let's take a look at butane. All right. Now with butane, we've got 4 carbons, and what we're going to do is we're going to take a look at the conformational analysis between carbons 2 and 3. Now that's another very important thing that you should keep in mind. Whenever you're asked to do a conformational analysis, you must know the bonds which you're analyzing. All right? In other words, as we saw with ethane, what we're doing essentially is we're sort of analyzing the stability of the locations or the probability of the locations of the substituents on the 2 carbons. All right? So in this case here, you have in a more complicated molecule, you have to specify the carbons which you're or rather the bond around which you're doing this conformational analysis. So in this case here, we're looking at carbons 2 and 3. Okay? So what we're going to do is we're going to take this molecule, as it's represented in the wedge and dash, and we're going to rotate it out of the plane of the board. All right? And this is what we get. So if we rotate this out of the plane of the board, this methyl group is going to be sticking up. All right? We're going to have a hydrogen pointing out this way and a hydrogen pointing out this way on carbon 2. All right? At the same time, as we rotate this out of the plane of the board, the methyl group is going to be pointing down on carbon, I'm sorry, I should have said carbon 3. Carbon 3. And we also have 2 hydrogens which are pointing out to different, to opposite sides. So this would represent one of the possible conformations of butane. Now, if you notice, we've sort of stumbled on the most stable conformation. The reason why this is the most stable conformation is because we've got the 2 larger groups as far away from each other as possible. We've got the 2 methyl groups, the ones which are most demanding in terms of space that they require, are as far away from each other as possible. This is what's referred to as the anti-conformation. All right. So in this molecule here, in N-butane, the anti-conformation around carbons 2 and 3 is the most stable. Now what we're going to do is we're going to rotate one of these carbons, and we're going to see how it affects the stability of the molecule. In other words, what happens to the stability or the energy content of the resulting conformers. Okay. So what we've done here is we've rotated. Wait a minute, can I see that other one again? Yeah, so what we're going to do is we're going to rotate carbon 1. All right? Okay. Okay, so we rotate carbon 1, and whenever you're doing these conformational analyses, just rotate one of the carbons. If you rotate two of the carbons, you're going to get completely tangled up and get lost. All right, so just rotate one of them. So what we've done is we've taken carbon 1 and we've rotated it 60 degrees in a clockwise direction. Now you notice what happens now is that the methyl group lines up with this hydrogen, and in fact all of the substituents line up. So we've actually entered into an eclipsed conformation. All right, now as I say here, it's bad, but it's not the worst. All right, the worst is yet to come. Okay, because we've got these groups, we've got these substituents lined up. Not a good situation. There's quite a bit of repulsion between them, but the worst is yet to come. All right, now, so what we're doing now is we're going to take this and we're going to rotate it another 60 degrees, and we get into this conformation here. Now, this is another staggered conformation, but because of the added substituents on this, we have yet another term. This is referred to as a gauche conformation. This is a gauche conformation. We've got everything sort of staggered, right? Nothing lines up. But at the same time, we've got the two big substituents right next to each other. So even though this is a lot better than an eclipse, it's not the best. This is nowhere near as good as the anti-conformation. Okay? So this is a gauche conformation. It's better, but not the best. Now, if we take this carbon 1, I should say carbon 2, and rotate it another 60 degrees, what's going to happen now is that we get the worst possible situation. All right? This is the worst possible situation because now we've got the two big, bulky methyl groups lining up. All right? There's a considerable amount of steric repulsion there, and as a result, this conformation of the molecule has the highest potential energy. Now, once again, this is a lot easier to see if you use your Newman projections. Let me just reconstruct this thing. All right, let's start off with the best. All right, now remember, what we're doing is we're looking at rotation around carbon 2 and 3. All right? So here's carbon 2, this is carbon 3, and this would represent our starting point, the anti-conformation. Wait a minute. I think I had it the other way around. All right, this would represent the anti-conformation. We've got the two methyl groups as far away from each other as possible. Now we take this and we rotate this 60 degrees. So now the methyl group is lining up with this hydrogen and all the other hydrogens are lining up. All right, this would represent an eclipsed. As I said before, this is not the worst eclipsed. All right. Rotated another 60 degrees, and now we have a staggered conformation. All right, and this particular staggered conformation, because of the proximity of these two large substituents, the methyl groups, this is referred to as a gauche conformation. Rotated another 60 degrees, and now we're into the worst possible situation. This is called the eclipse. This is another eclipse conformation where we have all of the groups lined up, including the two big bulky ones. This is the worst possible situation. Now, just as we saw with ethane, we can sort of symbolically track the changes in energy. So this would represent, as a function of rotation of that one of the carbons, so this would represent the this is an energy minimum. All right, we rotate at 60 degrees, we go into an eclipsed. Okay? Rotated another 60 degrees, we go into the gauche. Now, you notice that the gauche is actually a little bit more energetic, has a little bit more potential energy than our anti-conformation. Okay? We rotate it another 60 degrees, and we go into this eclipsed where we've got everything, including the two methyl groups, lining up. This would represent the energy maximum. This is the worst possible case for this molecule. This is the least favored of the conformations, this eclipsed where you have the two methyl groups lining up with each other. Okay, so this is more complicated because we've actually got two minima and we've got two maxima. Okay, all right, now one of the things that you're going to have to be able to do is to look at a molecule and determine what the most or the least stable conformation is. In this case here, we've got a slightly more complicated molecule. This is 2-methylpentane. Okay? And what we're going to do is we're going to analyze, we're going to try to find out what the most stable conformation is around carbons 2 and 3. Okay? All right, so once again, we rotate this out of the plane. All right, in this case here, we're rotating it this way because I wanted to put the 2 out here. Doesn't really make any difference. All right, you could rotate it either this way or this way. Just make sure you keep it straight. Okay, just make sure you keep track of what you're doing. Okay, so we rotate this out, and this is the resulting Newman projection. We've got this methyl group pointing up. Okay, we've got this methyl group pointing out. We've got a hydrogen pointing out like this. Okay, with this carbon, we've got 2 hydrogens coming off, and we have this ethyl group. Okay, so the ethyl group is going to be pointing straight down, and then we've got the 2 hydrogens out like this. Now, is this the best possible situation? Okay. Now, let's just take a look at something. Supposing we took this and we rotated this around to here. Okay. I mean, obviously, an eclipse is not going to be the most stable. So we're only considering gauche or staggered conformations. If we take this and rotate it, if we take carbon 1 and rotate it so that this carbon is here, or this methyl group is over here, and this methyl group is over here, we get this conformation over here. The question is, which is better? Well, it turns out that this one is better because even though you've got a fair amount of crowding here, this ethyl group is only next to one of the methyls. All right? In B, if you notice, what happens here is that the ethyl group, which is fairly large, okay, it's fairly demanding in terms of the space it requires. The ethyl group now is close to 2 of the methyl groups, so this is going to be the less favored of these 2 conformations. They're both gauche conformations, but this one is going to be somewhat more stable than this one over here. It'll be somewhat more favored. Now, is it possible to get an anti-conformation here? The answer is no. Okay, an anti-conformation is not possible in this molecule. You can't get this ethyl group any further away from the methyl groups than this conformation here. If we rotated this up here, we would end up with yet another. We'd end up with another gauche conformation. Okay. In other words, if we rotated this up to this point here, it would just be the same as this, essentially. Okay. All right. So these Newman projections are something that you're going to see when we talk about the pathways that various reactions take, because this is going to determine the stability of the particular conformation is going to determine how the molecule will line up as it's going into a particular reaction. That will have a profound effect on where are the substituents, where the actual chemistry takes place in the molecule. Okay. Thanks very much.